Okay, hello and welcome back. So today, after having learned about SU2s, we shall take a step forward and try and learn about more general Lie algebras. Okay, so the construction will be very similar to SU2s in the sense that we will be using the things that we have learned in the SU2 in specifically the way the representation theory works with these uh, with trying to label things with some JZ, and then there were raising and lowering operators, and so on and so forth. So we shall, we shall focus our attention on trying to use these lessons that we have learned from the SU2 and see how far these can be generalized for the other higher, higher Lie algebras. Okay. So now, so as I say here, we read generalized analysis of the representation of the SU2 algebra to an arbitrary simple Lie algebra. Okay. For this, we adopt quantum mechanical ideas. So we find the largest set of commuting Hermitian observables, and we will use their eigenvalues to label the state. So you would remember there's something called CSCO, complete set of commuting observables. So we will use that particular idea. So, so our observation would be that the largest set. So our observables rather would be the largest set of Hermitian operators that commute with each other. So these will be, as you can understand, simultaneously diagonalizable, and the eigenvalues will thus be analogous to that of what we call JZ or J3. Rest of the generators would be like the raising and lowering operators that you have in the SU2. Okay. So we what we will find is that there is to every raising operator there corresponds to there is going to be a corresponding SU2 subgroup, and we will learn. We will, as I say here again, we'll use SU2 to learn about this larger algebra. Okay. Now, so a set of commuting Hermitian observables, which is as large as uh, possible in this Lie algebra, is going to be called a Cartan subalgebra. Okay. Uh, and this is going to be essentially unique, so we can anyone will choose who's going to give you similar, same results. And in a sense, if you have two sets, there's one with five generators, and there's another one with five generators. It will one can show that the results. So the representation theory is going to be blind to which one of these two you use. Okay, so now what we are going to be doing is that in a particular irreducible representation D, we will look at the number of Hermitian generators. These we will call Hi, and where I runs over 1 to n. This is these form the Cartan subalgebra, and these HIs will be called Cartan generators. As you can understand, HIs are going to be Hermitian, and the HIs will commute amongst themselves. That means HI will be equal to 0. So these Cartan generators will form a linear space, and there what we will do, we will choose a basis where this will satisfy trace of HYHJ is equal to delta IJ into some number in front of this. This depends on the representation and the normalization of the generators and so on and so forth. Okay, so this was my Cartan subalgebra. And so the number m, so the number of independent Cartan generators is going to be called the rank of the algebra. Okay. The Cartan subalgebra, as we just said, is these. So these all will be generators that commute with themselves. So what is going to happen is that so these are going to be simultaneously diagonalizable. The states of the representation thus can be written as something which is mu x and t, where hi acting on this is going to give you mu I. Okay. So d labels the labels the representations, and x can be any other label that is there. Okay. So these eigenvalues mu I are the ones which are called the weights. Okay, these are the weights, and as these hi's are, I mean, Hermitian, as they are, so they are. So these are eigenvalues of Hermitian operators. So these have to be real. Okay. So the m component vector that you are going to get with each of these entries mu I, this whole thing is going to be called the weight vector. Okay, this is called the weight vector. Very good. Now what we're going to do is we're going to focus on the adjoint representation. Remember the adjoint representation, the generators TA, what is happening is when you write them out as matrices, they become the structure constants with some factors of phi. Okay, so the rows and columns of the matrices that are labeled by the same index, the rows of column of the matrices are labeled by the same index that labels the generators. So the states, if you wish, of the adjoint representation correspond to the generators themselves. Okay, so what we will do is we are going to look at the state that corresponds to an arbitrary generator xa, and we are going to call this the state xa. Okay, so you can find linear combinations. So xa, alpha xa plus beta xb is going to be this particular state. It's going to be very similar, of course, because what is happening is, since the generators form the vector space, these states will do the same. All right, so now our convenient scalar product in this case is going to be defined like this. So the lambda is there's going to be some particular number. Okay. All right, so now let's look at the action of the generator xa on the state xb. Okay. Now the net, so this is, you can think of this as a sum. So you're inserting a complete uh, set of states here, and so this is equal to this, because remember, of course, if you have something, an identity is going to be this, right? xa. So this is identity. So summation c. This is equal to identity. Now, so you've inserted this in. The sum over c is implied. So what you get is that you end up with xc, and xaxb, right? Now remember what this is going to be. So this is going to be xa acting on xb, but also remember that this is also, so this is going to be the matrix element between c and b of xa. So this is just what? So this is just TA, if you wish, and it's between C and B, so it has to be CV. So this is TACB. Remember that this is just just by looking at the stuff earlier. This is minus I ACB XC. You move these particular indices around, and you pick up a minus sign. So this becomes IFABC XC. Now, as you can see from our linear combinations above, you can now take this thing inside. So this becomes a new new vector here. So this is a new state. Uh, well, it's not really new state in that way, but so you can do this particular operation because these guys again are going to form a vector space. Now, what is IFABC XC? This is just XA with XB, right? So the commutator of XA with XB is IFABCXC. So what you end up with is the action of XA on the state XB gives you the state of commutator of XA XB. So this is something that we should keep in mind. All right, and as we go ahead, this was important. Now, what are roots? Roots are going to be the weights in the adjoint representation. Okay, this particular thing is extremely important. Also remember, since hi and hj gives you 0, the states which correspond to the Cartan generators will have 0 weight. How do we see this? Hi with hj. So remember that the roots where the eigenvalues of the hi on these states in some particular representation. Now we chose that the representation is going to be the adjoint representation, and we saw that in the adjoint representation, xa's are just labeled by the by this arbitrary generator. So when you are looking at states that correspond to the Cartan subalgebra, those will be given by the state hj. So you will have the action of hi on hj. Now we have just proved the action of some xa on a state xb is given by the commutator of xa xb. So this gives you hi with hj, which is essentially equal to 0. Okay. Now all the states, so now all the states in the adjoint representation with 0 weight corresponds to, so all states in the adjoint representation that have 0 weight corresponds to these Cartan generators. Also, so what you also need to remember that these are also going to be orthogonal. Okay. All right. Now, the other states in the adjoint representation, which do not correspond to these Cartan generators, will have some non-zero weight vectors. Okay. So you have HIs, and you want to look at these E alphas. So E alphas are the states which belong to the other generators. So these E alphas are going to give you some alpha I times E alpha. So the corresponding generators will satisfy hi with E alpha is alpha I E alpha. And these non-zero weight vectors will uniquely specify these states. Okay. Just like you do with SU2, there are these just like you have in the SU2 for raising and lowering operators, these E alphas are also not going to be Hermitian. How do you see that? So you take this this particular equation and you take the dagger of this equation. Okay. So the dagger of this equation gives you hi with E alpha. E alpha dagger is minus alpha I E alpha, and it's very clear from this and this that E alpha dagger is actually E of minus alpha. Okay. So this should be very reminiscent of things like J plus and J minus of the raising and lowering operators of SU2. We're going to push forward with this and try and understand this a little bit more. And we will understand that these guys are actually, very similar to J plus and J minus as we just go ahead. Okay. So the states which have different weights must also be orthogonal, right? Because they would have different eigenvalues for at least one of the, HIs. So what we can do is we can sort of choose the, choose the normalization of these E alphas such that this is equal to delta of alpha beta. Okay. So these alpha i's, alphas, alpha i's are called the roots, as we said earlier, and these the um, so this this vector alpha is going to be, I mean, called the root vector. Okay, so let me actually not say, even though um, this is a weight vector, but in the adjoint representation. But let's say that the vector alpha with, I mean, uh, so this is, so when you're looking at, uh, as we said before, roots are going to be the weights in the adjoint representation. So the root vector is essentially the weight vector in the adjoint representation. Okay, very good. All right, moving on. So let's try and see that these alpha, this E alpha plus minuses are essentially the raising and lowering operators. So yeah, this again, the scan has not been very great. So these are E alphas, E plus minus alphas. So let's look at this. So HI acting on E alpha, and let's say this is acting on the state which has which is mu and D. So this is mu and D in this representation. So it should, by our previous arguments, well, not by our previous arguments, but this is very clearly HI of comma E alpha, E plus minus alpha of mu D plus E alpha, E plus minus alpha HI on this mu D, right? Now, what is this? So HI with E alpha, E plus minus alpha, is just simply going to be, so this is going to give you, so E plus minus alpha on mu D. And remember that if you look at uh, this, so H with E alpha gives you alpha E alpha. So this is going to give you, so depending on what this guy is, so this is going to give you alpha times E alpha, or plus minus alpha times E plus minus alpha. And HI on mu D is just mu. So this is going to be mu plus minus alpha, right? So let's just highlight this again. The scan is not great, so let me try to highlight this. So this is mu plus minus alpha E alpha. So this either raises, so HI either raises or, lowers the eigenvalue. So these are clearly either raising or lowering operators, but it's important to mention that at this point we don't really have a notion of positivity. So it doesn't really make sense which one is called the raising operator and which one is called the lowering operator. Now let's do something more fun. Okay, let's look at the action of E plus alpha on the state E minus alpha. Okay, so what's this going to do? So this is going to be this state, just by what we have, is going to have a weight of alpha minus alpha. This has to be equal to 0. Okay, so since the weight of this has to be 0, this has to be a linear combination of states that correspond to these. I mean, these Cartman generators, right? So E alpha, what do we have? E alpha acting on E of minus alpha generates a state which has, uh, weight alpha minus alpha. Uh, so this gives you, so this is 0. So this has to be some linear combination. So beta I of some states H alpha, Hi. So, sum over I is again implied. So this is equal to, so you can take these things inside now, beta I Hi. And this is going to be given, this is just beta dot H if you wish, of the two vectors. And we know from before that, the action of this is just, the state is also just E of minus alpha. That's E of alpha with E of minus alpha, right? Okay. What are beta i's? So beta i's are simply, so you can take this on the other side. This is Hi, E alpha of E of minus alpha. That's great. So this is EI. So this is HI acting on E alpha, E minus alpha. Right? Now, this is just a trace. This is just a trace. So this is my lambda inverse. Trace of HI, E alpha, E minus alpha. This is just normalizing things, right? So that's, if you had these two, vectors, that's how you would do it. Now remember that you can move things under a trace, so you can just write this out and use the cyclicity of the trace to move the generators around, and then you will have E of minus alpha of Hi, E of alpha. Okay, and then you'll just have the lambda i's, so lambda minuses, and Hi with E alpha is just alpha I, so that goes out, and there's this trace of E alpha, E minus alpha with, sorry, let's get this right, E minus alpha with E alpha, and that is going to be, what we will do. So now, so that just amounts to alpha I, right? This is the trace rules that we had earlier. So that's simple in the sense that what we get at the end of the day, in that case, is that, so what we have achieved is we have been able to show that E alpha with E minus alpha with E of minus alpha gives you alpha dot h. This is again very, very similar to what we had earlier when we were looking at the SU2s. So J plus with J minus gave you J3. Okay, you should be reminded of that from here. So okay, for the moment, I think I will let you. I'll stop here, and this was a very first you know first introduction, if you wish, first look at roots and weights, and so just remind yourselves of what it is, and we shall go ahead with this in the next lecture and build a little bit more before we actually try and understand SU3. Okay, so the idea is essentially we will be trying to build on what we had done for the representation of SU2 and trying to apply this to an arbitrary simple Lie algebra. Okay, so that's it for the moment, and again we shall get back to this. So the next lecture gives you a little bit more of roots and weights before we go on to trying to describe SU3s. So then we will move on to the Lorentz algebra. I mean, before that, we'll have a little bit of a special theory of relativity and how group theory. So we will try and link that up with group theory, and so that's going to be sort of the end of the part of group theory. So another 2 to 3 lectures, depending on how long the lectures are. So that should be it. Okay, so that's it for the moment then, and there'll be more soon.